Hello viewers, welcome to this next lecture on the MOOC course on mathematical portfolio theory. You would recall that in the last two classes we have been focusing on mostly talking about financial markets and we talked about derivatives, and in the previous class we mostly looked at the two main kinds of assets. One was the risky asset, an example of which was bond, and the other was a risk free asset and which was a stock. So, what we are going to do now is basically that we are now going to consider some asset pricing model, and for that purpose we are talking about the risky assets, and in particular we will look at two models, namely the binomial model and the geometric Brownian motion model, which are respectively the discrete and continuous models for asset pricing that are most commonly in use. So, we begin this lecture by first talking about the binomial asset pricing model, for which we will make use of the binomial distribution, and then we will talk about the geometric Brownian motion, which will be driven by the normal distribution, which justifies the introduction of these two distributions in one of our earlier classes. So, we start this lecture. So, the topic of this lecture is binomial and geometric Brownian motion or gBm asset pricing model. So, let us first begin with the binomial model. So, we consider this important model for modeling the stock price movement. Now, note that this model, while being mathematically tractable and simple, is still able to capture many aspects of markets in the real world. So, we first consider the model in the paradigm of one step and define it through the following conditions. So, before I start with the condition, let me just say that we are basically will look at some time points 0, 1, 2 and so on. So, these are just the index for the different time points. So, we start looking at the first condition. So, the one step return Kn on a stock are. So, what do you mean by return? So, just to illustrate it through a simple example, suppose that you invest an amount of 100 today and then at the end of 1 year it becomes 110. So, this means that you have made an additional amount of 10 in 1 year upon your original investment of 100. So, basically this will be given by 110 minus 100 divided by 100. So, Kn here basically will mean that it is going to be the difference in the stock price between two subsequent two consecutive stock prices at two different times and divided by the price at the previous time. So, suppose we take some time point n and n plus 1, then the return in this particular time interval will be given by the stock price at time n plus 1 minus the stock price at time n divided by the stock price at time n. So, then this particular return is going to be a random variable. So, these are IID random variable. So, this return Kn, these are all random variables such that Kn is going to be equal to u with probability p and d with probability 1 minus p. So, this means that if the stock price today is say S of n, this means that tomorrow the stock price can be S of n multiplied by 1 plus u with probability p, or it could become S of n into 1 plus d with probability 1 minus p. So, this essentially what it does is that between any two time intervals or any two time points, the change in the stock price can only happen in two possible ways. One, when it is changes by a factor of 1 plus u, and one when it changes by a factor of 1 plus d, and since these are random variables. So, we take the corresponding probabilities to be p and 1 minus p respectively. So, now this will happen at each time step n, where I need to put this condition. So, one of the condition would be a 1 less than d less than u, all right, and the second is 0 less than p less than 1. So, we take the condition minus 1 less than d less than u, the reason being that I want first of all that 1 plus d should be greater than 0. So, that the stock price, and also then I need obviously 1 plus u is greater than 0. So, that the stock price at the next time point, when it is obtained by either multiplying by 1 plus u and 1 plus d, will still end up giving you the price of the stock to be positive. And I need 0 strictly less than p less than 1, and the reason I cannot allow p to be equal to 0 or 1, because if either p equal to 0 or p equal to 1, that means the return k of n is no longer going to be a random variable, and then it will become a certain return, and then it will start acting like a bond. So, next this implies that the stock price. So, just to sum up whatever I have said, this implies that the stock price S n can move up or down by factor 1 plus u or 1 plus d respectively at each time step. So, here typically u is what is known as the up factor and d is what is known as the down factor. So, typically we say that the stock price from the current time of S n, in the next time point, it can either go up to S of n into 1 plus u with probability p, or it can come down to S of n into 1 plus d with probability of 1 minus p. So, then note that the condition. So, as I had mentioned before, this condition of minus 1 less than d less than u guarantees that if you start off with a positive stock price, then S of n will also be positive for all n. Now, further we let R be the risk free rate for a single time step. So, R being the risk free rate basically means that if you invest an amount of S0 in a bond today, and R is the interest rate that is prevailing for a single time period, then at the end of that time period you will receive an amount of S0 into 1 plus R. We now come to the second condition, and this condition will be in terms of this R that we have just introduced. So, the second condition involves the assumption is that R is the same at each time step. So, that means R remains constant as long as you are considering the model of the asset, and D less than R less than U. So, if we consider the times say 0 and 1 and the respective stock prices S0 and S1, then by definition what will we get? We will get, so by definition k of 1 is going to be equal to S of 1 minus S0 divided by S0, and this implies is that S of 1 is equal to S0 into 1 plus k of 1. So, the random variable, now remember that k of n and in particular k of 1 can take two values. So, the random variable S1 then can take the values S1 is equal to S0 into 1 plus u and S0 into 1 plus d with probability p and with probability 1 minus p. So, here I would like to just make one more observation that we had this condition that minus 1 less than d less than u, and then I put in r in between. So, the reason why this is very crucial. So, I have already explained why we must have d greater than minus 1, because we need 1 plus d to be positive, resulting in the stock price at all subsequent points being positive if we start off with a positive stock price. And by the same logic, I need 1 plus d to be 1 plus u to be greater than 0, so that the stock price remains positive at all subsequent points. Now, the third point that we have just introduced in the second condition, where basically R lies between D and U. The reason for this is that suppose that R is less than D less than U. So, this means that the return in the, so the stock price in any single time interval can either go up by a factor of 1 plus U or come down by a factor of 1 plus D. Now, if my R is less than both D and U, this means that if I invest in the stock, in the worst case scenario, I will end up with S0 into 1 plus D, but as in comparison to that, if I invest in a risk free asset, that is a bond, then I will end up with S0 into 1 plus R. So, this would mean that S0 into 1 plus R is less than S0 into 1 plus D, which is less than S0 into 1 plus U. So, this means that in the worst case scenario, the stock price will still be higher at the end of the time period as compared to an investment in a bond, which cannot happen because the stock is a risky asset. And also we need my R to be less than U, because if R is greater than U, this means that your return on a risk free investment is always going to be more than the best case scenario, that is S0 into 1 plus U in case of a risky asset, which leaves no incentive for anyone to invest in the risky asset, because an investment in a risk free asset at a return of R obviously is always going to be higher. So, these two cases ruled out, you basically then need that your R must lie between D and U in both the cases. Okay. So, now what you do is that I have just looked at the scenario when I look at some time point indexed by 0 and 1, and now let us look at some n time points. So, suppose that we are looking at a stock price say over a time interval, and suppose you are looking at time points 0, 1, 2, 3, this could be days, first day, second day and so on. So, suppose we consider a general scenario and try to see what is going to be if you start off with a stock price of S of 0, which is deterministic. So, in this case your S of 0 is known, it is deterministic, it is only S of 1 that is random, because sitting at time t equal to 0, you do not know for certainty with what S1 is going to be. So, likewise, instead of just considering the time point 0 and 1, we consider some generic time point small n and look at what the stock price is likely to be, or what are the possible stock prices that we can have at time n, that is, what are the possible candidates for S of n if we start off with the initial stock price, namely S of 0. So, accordingly, in case of an n step tree of stock prices, we consider the scenario of I upward, that is I number of 1 plus u, and n minus I downward movement. So, this produces the same stock price as 0 into 1 plus u raised to I into 1 plus d raised to n minus I at time n. So, this means that say you have this time interval 0, 1, 2 all the way to time point n, and I say that as we move from 0 to n, while reaching there you will basically have I number of cases of 1 plus u's, and you will have consequently n minus I number of cases of 1 plus d movements. And so, consequently the stock price is then going to be S 0 into 1 plus u raised to I into 1 plus d raised to n minus I, where your I can be 0, 1, 2 all the way to n. So, this means that you could have, if I is equal to 0, that means that right from the beginning to the end there is going to be no upward movement, and it is going to be all downward movement. If I is equal to 1, that means in this from 0 to n you will have only one upward movement at some single time step, and for the remaining time steps you will just have all downward movements and so on. So, generically if you are looking at n steps and you start off with S 0 and you want to see what the stock price is going to be at the end of n steps, where between 0 to n you have I number of up movements and n minus I number of down movements, this is what you are going to end up with, S 0 into 1 plus u raised to I into 1 plus d raised to n minus I. So, accordingly, now there are n choose 1 such scenarios. So, this means that between in the n time intervals that are between 0 to n, you can have I number of ups in many different ways. It could be that the first I movements from step 0 to I you have all up movements. It could be that the last I step, it could be that there are alternative type steps. So, there are different in a sequence in which you can have I number of upward movements, and the number of such possible combinations is going to, out of this n, is going to be n choose I. And since there are n choose I such scenarios of I upward movement and n minus I downward movement, so this means that this means that it will have the probability of each scenario being. So, remember that the movement from one time step to another time step, whether it is an upward or a downward movement, they are all independent of each other. So, this means that the probability of I upward movement is going to be given by p raised to I, and the consequent n minus I downward movement will be given by 1 minus p raised to n minus I. So, that means that there are n such scenarios with the probability of each scenario being p raised to I into 1 minus p raised to n minus I. So, now we have both the identifiers as far as the stock price S of n is concerned. We know what is going to be the stock price, and we also know what is going to be the corresponding probability. So, this means that I can write S of n is going to be S0 into 1 plus u raised to I into 1 plus d raised to n minus I with probability p raised to I 1 minus p raised to n minus I, and this can happen in n choose I number of ways, and this can hold for I is equal to 0, 1, 2 all the way to n. So, therefore, the stock price Sn is obviously a discrete random variable with n plus 1 different values. So, I just conclude the discussion with a graphical representation for n is equal to 2. So, suppose that we start off with S naught. So, according to the binomial model, we can go up to S naught into 1 plus u with probability p, or go down to S naught into 1 plus d with probability 1 minus p. Now, again from here I can go up to S naught into 1 plus u into 1 plus u, which is 1 plus u square, and this probability is going to be p, or I can go down to S naught into 1 plus u, which is the existing price, multiplied by 1 plus d. Similarly, here when I start off with the existing price S naught into 1 plus d, I can go up to S naught into 1 plus d into 1 plus u, and note that these are both equal. And so, the probability here is going to be 1 minus p, this is p, and here with probability 1 minus p, I can go down from S naught into 1 plus d to S naught into 1 plus d square. So, that is how we generically end up with our formula for S naught into 1 plus u raised to I into 1 plus d raised to n minus I. So, here n is equal to 2. So, for I equal to 0, we have this. So, this is when n equal to 2 and I is equal to 0. This is the scenario when n is equal to 2 and I is equal to 1, and this is the scenario when n is equal to 2 and I is going to be equal to 2. Okay, so, this concludes the discussion on the binomial model. So, next we look at the other model, which is the geometric Brownian motion, gBm asset pricing model. Okay, so let me first of all start with a motivation for this, from the point of view of it being extended from the binomial model. So, the primary motivation is that the discrete time pricing models clearly have the disadvantage of being restrictive in terms of the range of asset price movement, as well as the time intervals at which the asset price movement can take place. So, let me explain these 2 points in a slight amount of detail. So, the first disadvantage, I said that it is restrictive in terms of range of asset price movement. So, it is easily sort of observable from the previous discussion regarding that if you start off with an amount of S0 at time 0 and then you want to look at the asset price Sn, and we saw that this is going to be S naught into 1 plus u raised to I into 1 plus d raised to n minus I. So, this means that after if you are looking at a n point n time interval discrete model, then you end up with only n plus 1 possible values of the stock price, which are the random variables at time n. So, this means that you only have a limited number of possible stock price, which is not consistent with what actually happens in the real world. And secondly, you are talking about the time points at which the stock prices can change. So, we are talking about some time point 0, 1, 2, perhaps on a daily basis. But given the way stocks are traded now, this is more of a continuous process, and what this binomial model does is that it actually restricts the time point at which the stock prices can change. So, in order to address these two key shortcomings of the binomial model, a natural way is to move on to the continuous time model. So, this can take place. Okay, so, accordingly, we will now consider the continuous time limit of the binomial model. So, what we do is that we consider a sequence of binomial tree models, each with time step being tau is equal to 1 over n, and then take the continuous time limit by letting n tends to infinity. So, what this means is that we basically look at some time length of 1 and we divide it into n number of subintervals. So, the length of each of those subintervals is going to be 1 over n. So, suppose we take our time interval of 1 year and we want to look at the asset price movement over 1 year, and we take n equal to 2. So, that means tau is going to be equal to half a year, which is 6 months. Then we take say n equal to 12, that means tau is going to be 1 month. If we take n equal to 365, then tau is going to be equal to 1 day. So, what we do is that we basically look at various different scenarios of such binomial models with different values of n, and as we increase n, we observe that the time interval between any two consecutive asset price movement, which is given by tau, that becomes smaller and smaller, and as your n tends to infinity, your tau basically tends to 0. So, that means that the asset price movement model now is effectively a continuous time model, because the time interval between any two price movement, it tends to 0. So, what we are going to do is that we will look at a binomial model for asset pricing with n, and then we make n smaller and smaller and let n tends to infinity, and that would give us a continuous approximation of the binomial model, which in turn is going to result in the geometric Brownian motion for asset pricing. Okay, so, now what you do is that we make a note that we will have to make a simplifying assumptions so that the proof is accessible. So, for the approximating sequence, we will make the assumption that the probability of the upward and the downward movement of the asset price are equal to half each. That means, we take p is equal to half and 1 minus p equal to half. Okay, so, now we recall that. So, recall the notation Kn, which denoted the return at the nth time step. Now, for the sake of convenience, and we will later on see why this needs to be done, we introduce what is known as the logarithmic return. So, logarithmic return is nothing but the natural log. Remember, in finance, log always means natural log, that is base e. So, the natural log of 1 plus Kn, I will define this to be the logarithmic return, which is small kn, and this will be nothing but, this can take the value ln of 1 plus u and ln of 1 plus d, and remember here we took the probabilities to be identical. So, Kn can have probability half and half in the two scenarios. So, from now on we will primarily be using the logarithmic return. Now, another aspect, so I will make another observation here. So, the another aspect to be taken into account is that we consider the continuous compounding convention. So, to see this in more detail, we suppose that we start off with an amount S naught, which we invest at the risk free rate or the rate of the bonds R per annum for say t number of years, and with the compounding happening m times a year. So, this means that I have this interval 0 to capital T, and this is 1 year, 2 year and so on, and in each year I compute the interest m number of times. So, this means that if I start off with an amount of S naught, then how will I do the compounding? So, for each period we will do the compounding. So, if R is the annual interest rate, then the per period interest rate is R by m. So, that means for the whole year it is going to be 1 plus R by m for each period raised to m. So, this is the amount of money that I am going to get starting off with an amount of S naught. So, slight correction, I start off with S naught. So, this is the amount of money that I will get at the end of 1 year. So, at the end of t years I will get the power to be m of t. So, then I can write, so then I can make the statement that at time capital T we accumulate an amount given by S of t is equal to S naught into 1 plus R by m raised to m t. Now, if I want to do continuous compounding, this means that you are basically having the interest is being calculated on a continuous basis. So, this means that I will take as m tends to infinity for continuous compounding. What do you get? Then what is going to be S of t if you start off with S naught? So, this is going to be S of 0 into limit 1 plus R over m raised to m t as m tends to infinity, and this can be written as limit m tends to infinity 1 plus R over m raised to m over R whole thing raised to R t, and this limit you know is the exponent. So, this is going to be e raised to R t. Now, here I took t to be some fixed number of years, but it is true in general for any other time point. So, that means that if your r is the interest rate, then at any, and you start off with an amount of S0, then you can see that at time small t, your S of t is going to be S naught into e raised to r of small t. Okay, so let us now come back to our main discussion on the gBm. So, accordingly, we take the return over a time interval. Remember, we took the time interval notation to be tau is equal to 1 by n. So, we take a time interval of length tau as e raised to r tau. Okay, so let m and sigma denote the expectation. So, I move on to the next step and I will introduce two variables. So, denote the expectation and standard deviation respectively, and these are yet to be determined. Remember the, so here at this point we do not know what m and sigma. So, these are the expectation standard deviation respectively of what random variable k1 plus k2 all the way to kn. So, this is basically the sum of the log returns of each individual intervals, and this is over a unit time window of 0, 1. So, just recall that you had n time steps, and so that is we had tau, that is each time interval to be 1 over n. Now, since your original return k1, k2 all the way to k of capital N, they were, remember that they were IIDs because they were modeled through the binomial model, and so they were independent, and so they are identically distributed, and of course they are independent because we assume that the change in the asset price between any two consecutive time steps, they are all independent of each other, and they of course follow the identical binomial distribution. So, for capital K1 through capital Kn, which was the original variable for the distribution, so I can, since these are IIDs, so consequently I can say that, so the variables K1, so the random variables small k1, that is the log return through small kn, are also independent and identically distributed. Okay. Now, let us go back to this. I said that m is the expectation of this random variable. So, that means I can write this as m is equal to expected value of k1 all the way to kn, and this by the linearity property of expectation. So, this is where we use the linearity property of expectation that we discussed earlier. And now, since these are all independent and identically distributed, they are basically going to have the identical mean of, say, E of some generic kn, and there are n number of such variables. So, this will be n of E kn. Similarly, sigma square is what? It is basically variance of k1 all the way to k of n, and this is going to be nothing but variance. Now, again these are, since these are independent, so the covariance terms will not show up. So, this is going to be simply nothing but n into variance of k of n. So, therefore, variance of k of n from this relation will become equal to sigma square over n, and remember n is 1 over tau. So, this becomes sigma square over tau. So, therefore, the standard deviation of k n, this is going to be nothing but the square root of this term, which is sigma into square root of tau. And please remember that these two, these will all hold for each n. Okay. Now, here we will essentially look at a slightly simplifying assumption. So, here what you do is that, so we have seen that the expected value of k n is m tau. So, here I just forgot to add this here. So, this will imply that, so therefore, expected value of k of n is equal to m over n, which is equal to m tau. Okay. So, now here the two possible values of each k n are. So, I make a total obvious choice. So, I want to figure out what my random variable k n is going to be in terms of this m and sigma. So, two possible values of each k n are. So, this is going to be ln of 1 plus u, this is going to be m of tau plus sigma square root of tau, and ln of 1 plus d, this is m of tau minus sigma square root of tau. So, you can actually verify that here the expectation, what is this going to be? This is going to be half into m tau plus sigma square root of tau plus half m tau plus sigma square minus sigma square root of tau, and this is just m tau. So, basically the expectation is going to be m tau for each of the k n, and we want to show that the standard deviation is sigma square root of tau. So, that also you can calculate easily. So, again just I use the definition. So, for this I will have variance of the random variable m tau plus sigma square root of tau minus the expected value of m tau square plus half, again I will have m tau, the other random variable, m tau minus sigma square root of tau minus the expected value of m tau square. So, this cancels out, this cancels out. So, this just simply becomes sigma square of tau. So, I have taken basically two particular cases, that is m tau plus sigma square root of tau and m tau minus sigma square root of tau. Okay. So, now we observe these two, and this motivates us to introduce a sequence of independent random variables, call them xi of n as, what is xi of n? Xi of n, I will define this to be plus square root of tau with probability half. So, this is motivated by the fact that this term and this term, the only difference is that of a sign, and this will be minus square root of tau with probability half. Now, once I have this definition of xi n, so I can actually combine these two possible values, and so then k n can be written as k n is equal to m tau, and then I have the sigma term. So, the only place where these are distinguished is plus square root of tau and minus square root of tau. So, I can write this as m tau plus xi of n into sigma. So, you can easily see that k n takes the value of m tau plus square root of tau sigma with probability half, and m tau minus square root of tau zeta n with probability half. So, this is zeta. Next, we introduce a sequence of random variables, say w of n. This is what is known as a symmetric random walk, such that, how do I define this? It is going to be nothing but sum of this zeta 1 plus all the way to xi n with W0. So, this is actually xi, I have been calling it zeta. So, please note that this is xi. So, here W0 is going to be 0 and xi of n, I can write this as W of n, which is the sum of xi's up to n, minus W n minus 1, which is the sum of xi's up to n minus 1, leaving only this xi of n. So, now I have found an equivalent representation of this random variable xi n, and I am calling this to be my difference between W n minus W n minus 1. Okay. So, consequently, so now what we do is that we first of all make a slight change of notation. So, we now use the notation t is equal to n tau for n is equal to 1, 2, so on. And consequently, my stock price S n and W of n that we have here and I have defined here, this will be written as S of t and W of t respectively. So, I will use the small w here. So, please note that this is the small w. Now, what is k n? Let us go back to k n. K n is natural log of 1 plus k of capital N. Now, what is capital K of n? This is just the S of n tau minus S of n minus 1 tau divided by S of n minus 1 tau. So, this is going to be natural log of 1 plus S of n tau divided by S of n minus 1 tau minus 1, this to cancel out. So, this will give me that S of n tau over S of n minus 1 tau, this is going to be nothing but e raised to k n. So, which implies that S of n tau is equal to S of n minus 1 tau into e raised to k n. So, accordingly, so recursively we will get S of t is equal to S of n tau is equal to S of n minus 1 tau into e raised to k n. This will be equal to S of n minus 2 tau e raised to k n plus k n minus 1, and I will keep doing this until I reach S naught, which is e raised to k 1 plus k 2 all the way to k n. Now, remember that my representation of k 1 through k n, what did I take? I have taken my random variable k n to be written in this form. So, I will make use of that. So, it is m tau plus xi n of sigma. So, this is going to be simply e raised to m n tau, that means there are n number of m taus, plus we have a tau, and then for k 1 I have xi 1 all the way to xi of n. And remember, what is this? What is n tau? N tau is t. So, this becomes e raised to m t plus this. So, this is actually sigma, not tau. So, plus sigma, and remember this xi 1 through xi n, this is defined as w of n, and so this becomes now sigma of w of t. Okay, so now we will make a Taylor series approximation. So, using the Taylor series expansion, what do I get? I will get that S of n plus 1 tau over S of n tau, this is e raised to k n plus 1, and I assume that k n plus 1 is small. So, I can approximate this as 1 plus k n plus 1 plus half of k n plus 1 whole square. We neglect the higher order terms here. So, this is going to give me now so what I need to take care of is we need to look at this term first. So, now k of n plus 1 square, what is k of n plus 1? K of n plus 1 is m of tau plus sigma xi n plus 1 whole square. Now, if we expand this, say you will have an m square tau square term here. So, that is order of tau square, and here you will have sigma square root of tau, because by definition of xi n plus 1. So, this will give you sigma square tau and the cross term. So, there will be tau here. So, the 2 m tau into sigma into square root of tau, that will give tau raised to 3 by 2. So, I ignored the square term and 3 raised to power term and retain only the sigma square xi n square term, which is tau, because xi n plus 1 is of the order of square root of tau. Okay, so, let me now come back to this. So, therefore, I have s of n plus 1 of tau by s of n tau. This is approximately going to be 1 plus k n plus 1, which I will now substitute as m tau plus sigma xi n plus 1 plus half, and this term I will replace with sigma square tau, and this I can rewrite it as 1 plus m plus half sigma square with a tau common factor plus sigma xi n plus 1. But recall that by definition xi n plus 1 is w of n plus 1 of tau minus w of n tau. So, therefore, from here we get, so n plus 1 tau is nothing but t plus tau over s of t. This is going to be 1 plus m plus half sigma square tau plus sigma into w t plus tau for this term minus w t, or this can be rewritten as s of t plus tau minus s of t is equal to m plus half sigma square s of t tau plus sigma into w t plus tau minus small w of t. So, these are small w's. Small w's. Okay, now one can make use of the central limit theorem, which we had mentioned in one of the earlier classes. We can show that as n tends to infinity, that is T n tends to t, or equivalently n T n tends to infinity, the following holds, that W n of T n tends to some capital W of t. And here this W of t, this is known as the Wiener process. So, what are the properties of Wiener process? So, the properties of Wiener process, the first property is W 0 is equal to 0. Secondly, W of t, it follows a normal distribution with mean 0 and variance of t. And thirdly, the increments, say W t 3 minus W t 2 and W t 2 minus W t 1 are independent for 0 less than or equal to t 1, less than or equal to t 2, less than or equal to t 3. So, this means that W of 0 is 0, W of t is a random variable which is a normal random variable. So, you see that is why we had to make use of we defined the normal distribution earlier. And the mean of this is 0 and the variance is t. And the last one, it says that if we consider two non-overlapping intervals T2 minus T1 to T2 and T2 to T3, then the corresponding increments of W T2 minus W T1 and W T3 minus W T2, these corresponding increments are independent of each other. So, once we have this definition, then we can now go back and look at this. So, what I am going to do is I am going to rewrite this. So, I will call this, so I take the small interval and this can be rewritten as ds of t. So, remember that this is the change in the interval. So, instead of t plus tau minus st, as n tends to infinity, your tau is obviously going to be 0. So, this becomes ds d of s of t. So, accordingly, this is going to be dst is equal to m plus half sigma square s of t and tau is dt. So, I will now replace tau by some small interval dt. So, then s of t plus tau minus s of t, this will become ds of t, and w small w of t plus tau minus some w of t, this becomes d capital W of t, because of the central limit theorem that I have just mentioned. So, this becomes m plus half sigma square s of t dt. So, from this term and plus sigma into dw of t. So, plus sigma into s of t into dw of t. And this s of t which shows up on both sides is because you have an s of t that was in the denominator. So, we had s of t plus tau minus s tau over s of t. So, that has come to the top part. Okay, now, we recall that s of t is equal to S0 into e raised to mt plus sigma of Wt. So, what we do now is, this is what we had done earlier and this is what we now follows as a limiting case of the binomial distribution. So, alternatively, it is customary to write, so let me call this equation 1. So, to write 1 as dst is equal to mu of st dt plus sigma of st dw of t. So, basically I will replace mu with I will use mu to replace m plus half sigma square. So, this is lot of times this is called drift and this is called the volatility of the asset. So, once you choose m is equal to m plus half sigma square equal to mu, so then the second relation accordingly becomes, so this has the solution s of t is equal to s naught. What is m? M is equal to mu minus half sigma square. So, this is e raised to mu minus half sigma square into t plus sigma w of t. And this is what is known as this is an example of what is known as the stochastic differential equation. So, if you had only these two terms, this would be an ordinary differential equation, but now that you have added this term which has the winner process which is a random variable. So, accordingly this becomes what is known as a stochastic differential equation and its solution under some conditions is going to be given by s of t equal to s naught e raised to mu minus half sigma square t plus sigma w t. Okay, so, just to do a recap, what we have done today is we looked at the binomial model and then we looked at a couple of shortcomings of the binomial model and then we moved on to the asset pricing model in the continuous time driven by winner process, and this is also what is known as the geometric Brownian motion. And this exercise today of discussing these things also highlights The background on probability theory that we have used, namely we looked at the binomial distribution, we have made use of the normal distribution, we mentioned about the central limit theorem and the properties of mean and variance. So, this brings us to the end of our discussion on markets and the asset pricing models that we discussed today. From the next class, we will start our discussion on the main topic for the course, and we will begin with the modern portfolio theory due to Markowitz. Thank you for watching.